Learning Outcome 4.8. Calculate Fourier transforms of periodic signals. You learned in Chapter 3 that Fourier series were for periodic signals, and only for periodic signals. At the beginning of Chapter 4, Fourier transforms were introduced as a way of expanding Fourier series to have an infinite period, and from that infinite period, they became aperiodic. And I hope that you're developing the intuition that when you hear the word periodic, you're thinking Fourier series and all the techniques that go with it. And when you see a aperiodic signal, that you're then thinking Fourier transforms and the techniques that go with that. In general, that's a very good way of dividing up your thoughts. However, you can also use Fourier transforms on periodic signals. This learning outcome introduces you to some of the techniques that do that. Please look at Table 4.2. There are several different transform pairs there, and transform pair 1 is specifically related to periodic signals. It says that if your time signal, x of t, is a sum for k equals minus infinity to plus infinity of a sub k e to the j k omega 0 t, that your x of j omega will be 2 pi times the sum for k equals minus infinity to infinity a sub k delta of omega minus k times omega naught. Does that first equation look familiar? I hope so. That's the synthesis equation for Fourier series. And we use this directly to convert something that's a Fourier series into a Fourier transform. If we know our Fourier series coefficients a sub k, we then know the Fourier transform. We're going to take those same a sub k, and we're going to multiply them each by an impulse. And we're going to scale that by 2 pi. These impulses occur spaced omega naught apart. Again, this should sound very familiar related to Fourier series, as your a sub k are spaced omega naught apart in a Fourier series. Note that omega is a continuous variable, and this delta function is a continuous impulse. Therefore, 2 pi is an area, not an amplitude. And really, the amplitude of this impulse is 2 pi times a sub k. So let's look at an example. This was example 3 from Learning Outcome 3.4. You had an x of t, which was cosine of 2t plus 3 sine of 4t. We determined that omega naught was 2. We applied Euler's and came up with our a sub k. We can now take these a sub k and use them with the first property of Table 4.2 to convert it into a Fourier transform. We're going to have a 2 pi for each term. We're then going to take our a sub k. If k is 1, our a sub k is 1/2. We then have our omega. Our k value is 1, and our omega naught value is 2. The next non-zero a sub k, again we start with 2 pi, has an a sub k value of 1/2, a k value of -1, and an omega naught value of 2. Our next non-zero a sub k occurs when k is 2, and it has an a sub k value of 3 divided by 2j, k value of 2, omega naught of 2. And our final non-zero a sub k has a value of minus 3 over 2j when k is equal to -2. And we can simplify this a little bit. We can also plot this. In Chapter 3, you plotted the magnitude of a sub k versus omega, and sometimes you plotted the phase of a sub k versus omega. We could do the same thing here, but since this is a continuous function, we much more often will just plot the value of x of j omega versus omega. Recall these are continuous impulse functions. This one is going to occur when omega minus 2 is equal to 0. That's going to be right here. This pi is an area, and it has an arrow to indicate that it's a continuous impulse function. The second term occurs when omega plus 2 is equal to 0. Again, an area of pi. Again, an arrow because it's a continuous impulse function. Our third term occurs when omega minus 4 is equal to 0. And our fourth term occurs when omega plus 4 is equal to 0. Notice that these areas are imaginary. It's a little bit sloppy mathematically, but it works, and it's something you commonly see when working with these things as an engineer. Okay, let's come back and think about this again. So if you look in table 4.2, transform pairs 3 says that if our time signal is cosine of omega naught t, our Fourier transform will be pi times delta of omega minus omega naught plus delta of omega plus omega naught. Transform pair 4 says if our time signal is sine of omega naught t, that our Fourier transform will be pi over j times delta of omega minus omega naught minus delta of omega plus omega naught. Recall that the Euler formula for cosine had a plus, and the Euler formula for sine had a minus. This occurrence of plus and minus is related to that. Hint, look at transform pair number 2, see if you can figure out where these derive from. Therefore, for our signal up above, our Fourier transform will be pi times delta of omega minus 2 plus delta of omega plus 2 plus 3, linearity, times pi over j, delta of omega minus 4 minus delta of omega plus 4. And this is the same result we had on the previous slide, just algebraically factored differently. Okay, what if our Fourier series had a constant in it, an A0 term? Note that transform pair number 5 from table 4.2 says that if our time signal is a constant, our Fourier transform will be 2 pi times delta of omega. Well, this makes some sense because we've been seeing that for every a sub k, we get a delta of omega minus k omega naught. This is our A0 term, so our k value is 0. So this is delta of omega minus 0 times omega naught, or just delta of omega. And we can just bring that right in there and use this transform pair together with transform pairs 3 and 4. And just add in one more term. And if we want to apply transform pair number 1 from table 4.2, based on our Fourier series coefficients, we can do that also. We get the same first pair, and we get that last pair with that k times omega naught. There are 2 more periodic time signals for which their transform pairs are listed in table 4.2. First one is transform pair number 6. If you haven't done so already, please take table 4.2 and number each of those transform pairs so we can refer to them by number and you can find them easier. Take a pencil right in there. It won't affect the resale value of your book, and as an engineer you should be keeping that book for when you're a professional. Transform pair number 6 has a time signal x of t that has a value of 1 when the absolute value of t is less than t1, and a value of 0 when the absolute value of t is between t1 and capital T over 2. It then states that x of t plus capital T is equal to x of t. This is what states that we've got a periodic signal. We're going to have a period of capital T. And that the transform of this is going to be the sum of k equals negative infinity to infinity, 2 sine of k omega naught t1 divided by k, delta of omega minus k omega naught. What's omega naught? It's related to capital T, your period, 2 pi over capital T. It hasn't changed any. Now if you're going to use this, you better know what it looks like. So let's think about that. If t is positive and the absolute value of t is less than t1, we're going to have a value of 1 from 0 to t1. But this considers the case where t could be negative, so we're going to have a value of 1 between 0 and negative t1. Okay, we know we're going to have a value of 0 when t is between T1 and capital T over 2, and likewise for the negative, because those absolute values, between negative T1 and negative T over 2. And because we know it's periodic, it's going to repeat itself. So all this is talking about is a rectangular pulse train. In your table of common Fourier series, it used to value W over 2 instead of T1. Same idea. And the transform is that sinc function. It should look very similar to what you see in your table of common Fourier series. And because it's periodic, the transform is going to have a whole bunch of impulse functions. Remember, omega is a continuous variable, so these are continuous impulse functions. They have an amplitude of infinity and are drawn with an arrow. Okay, transform pair number 7, x of t is the sum for n equals negative infinity to infinity, delta of t minus n capital T. So you need to know what that's going to look like, so let's draw a picture of it. Set your n value to 0. Delta of t minus 0, or just delta of t, that's going to be an impulse with an area of 1 at time 0. Set your n value to 1. Delta of t minus capital T. That's going to be an impulse where t equals capital T, just 1 unit over. If n is equal to 2, delta of t minus 2 cap t. So it's when t equals 2 cap t, and then we get 1 for negative 1, and for every other value of n. This is an infinite pulse train. We use this a lot in Chapter 7. And the Fourier transform of it is also going to be an infinite pulse train. Infinite number of impulses, but they're going to be located at 2 pi k over t, or instead of spacing them at 0, t, 2t, 3t, they're going to be at 0, 2 pi over t, 4 pi over t, 6 pi over t, 8 pi over t, negative 2 pi over t, negative 4 pi over t, etc. And instead of having an area of 1, they'll have an area of 2 pi over capital T. Draw it out. This is some of the things you can do with periodic signals using a Fourier transform. And since we tend to mix periodic signals and aperiodic signals, it's good to know how to do this with Fourier transforms and not just Fourier series.